able to make it to the lab today. Is,
Yes.
is there a addendum, or I remember there was something for people who are absent, usually for some labs, or will I just like tag along with the?
I'll check. I might have an addendum for that. I'm not sure if I do though, so I'll check. If you don't hear from me, just let me know after the break. Remember, we got spring break next week, so
Yeah, I got you. If there isn't one, can I just use the information my lab partner's got?
yes, absolutely.
All right, perfect.
Yeah,
Thank
it's
you.
better to, turn in a report at least so you only get counted for the absence.
Yeah.
Excuse me, Professor.
Yes, sir. Go have a go.
All
Was
right,
it
so
Angelo? Emilio?
I just got an email. I'm trying to clarify with you because I don't know if this is true or not. I'm gonna assume the email is true, but we just got an email sent out, the inclement weather update. I guess classes are closed at 3 p.m. I was just wondering if you got the same information, because if so, I'm gonna listen to you, but I'm
Yeah.
gonna drive home because if it's already closed, and I'm assuming the weather's gonna get worse, and I live like 45 minutes from here, so I want to try to get on the road as soon as possible.
Yeah, go ahead and get on the road. And in fact, since I just saw that text come across my transom too, so I think I'm going to have to go ahead and call this. But what I'm going to do is I'll make up a lecture in lieu of this. So there'll still be one. You can pay attention if you want, but you don't have to. And you guys are completely free to go. I'm just going to talk to the ether if no one's here. So you
Um,
can split if you want to, and I definitely don't want you risking life and limb to try to pay attention to me while you're driving. I'd much rather you just check it out later with the recording. Okay?
Okay. So it is true that it's at 3 o'clock. There's no classes after that.
Yeah, that's what I saw too on a text that came through.
Okay, I was just trying to make sure. Okay, yeah, because I'm gonna drive home because the wind's already starting to pick up, and I'm seeing like the tall trees moving and stuff.
Yeah, that's what
Um,
happened to me. I just drove home and I was blown all over the road. Luckily,
yeah,
The
it's not
yeah,
as bad as I thought. I haven't heard any lightning or seen thunder or vice versa. There is, nor have I
yeah.
seen any, hurricanes or twisters or anything like that. But yeah,
Yeah,
it's
that
definitely
makes
not
sense.
pretty.
Okay, I appreciate it, Professor. I'm gonna get on the road, and I'll get back online if you're still there when I get home.
That's cool. Have a good one,
Uh,
Emilio. Drive carefully, bud.
I appreciate it, Professor. Thank you. Goodbye.
You're welcome.
Uh,
Anybody else have any questions? Oh, William's here too. Let me get him in. Anyone else have any questions? All right. So what just happened was, and I don't even know if that text was from TCC or not. Let me double check. I saw it come through. No, that's not it. Uh, not that. Not that. Okay, maybe it was an email that I saw. Hmm. Inclement weather update. Yes. Due to inclement weather, TCC will close at 3 p.m. on Wednesday, March 5th. So, yes, the class is definitely closing at 3 p.m. So I'm going to go ahead and attempt to teach. Well, I'll start off by just taking questions on chapters 22 and anything before that as well. But I'm trying to go into chapter 23. I will make another video regarding chapter 23, no matter what happens here. But let me start off. Does anybody have any questions about chapter 22? Since I am making the actual test, there's a online test that I think I either already made it available or I'll be making it available right after class. But there's an online test that would have been due this coming Sunday, but I've pushed it back until after spring break, which is next week. So not this Sunday, but the Sunday after. There's an online test covering chapters 21 and 22. So that's why I'm asking anybody, do you have any questions regarding 21 or 22? Anything that's bothering you or any problems you couldn't solve in the practice test or anything like that?
Is it possible you could are you giving us a practice test for each chapter?
There are individual chapter practice tests. They just don't count for any kind of grade, but they're in the separate section that says chapter quizzes or something along those lines.
Okay.
I'll look at the actual wording to make sure I'm getting the right
So
stuff.
for those, I think I remember when I took those for the last test, you were
Hmm.
only allowed like 5 attempts, and they were only like they were the same questions. Is there a way you could put it in the same format that you did for the like overall practice test that you released before the test so we can get more like problems? or would you
Uh,
just say do the like homework ones?
Yeah, so yeah, I was just looking at it, and the module, by the way, is just called Chapter Practice. And I see, actually, I haven't even turned on Chapter 21 yet. I just went to turn it on, and I saw that Chapter 21 actually malfunctioned. So right after this, I will put on 21 and 22. I'm not going to change those formats, but the way I had it set up, I think I had three. I want to say I had two or three concept questions and then like one or two problems from the chapter. You can do it as many times as you want, and they're the exact same questions that are in my practice tests. It's just they come at different numbers. So what's going to
Okay.
happen is there will be a practice test. I was just double checking. Yo, I didn't make it available yet. There will be a practice test for chapters 21 and 22. And that is the best thing to prep for the online test and for the next face-to-face test. But until then, you can also use the chapter practice to focus on a single chapter. I don't want to change the format of those because it's exactly the right size where you can just do a couple when you have 5 or 10 minutes. Whereas the practice test is usually a little bit longer than the chapter practice, but not a whole lot.
Okay. All right. Thank you.
No problem. If you see me forget it or anything, feel free to send me a text because you know me, I'm a goober. So there's a good chance I might forget something, but I don't mean to. But there will be a online face to face, or excuse me, an online test, not face to face, that covers 21 and 22. But remember, all my chapters, or I mean, all my tests are somewhat comprehensive. So you'll see that you have the ability to be questioned on chapters 17 through 20 as well.
Yeah. Okay. Thank
Hey,
you.
no problem. Anybody else have a question? Okay. Well, the one thing I wanted to point out, and I pointed this out last night on my other 242 class. This is my online 242 class. I did post that video, by the way, but I need to edit it a little bit before I post it or make it visible. So I'll fix that today and repost it, but you'll see that video as well. The main thing that I want you guys to get out of the trend that is Gauss's law is Gauss's law is Gauss's law. It's always true, okay? But we normally use it in the physics and engineering world. We usually use Gauss's law in the differential equation form. In the calculus-based physics, we use it in the algebra, excuse me, in an integral equation form that says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. The what I want you to understand in that is there's only three types of problems that we can solve with Gauss's law using Gauss's law this way. And it's a very weird way. We are actively trying to solve for the integrand in the left-hand side of Gauss's law, but just the magnitude of it. So we sort of have to have some physical understanding of Coulomb's law and what that taught us so that we can hypothesize a actual electric field magnitude and direction and what it depends on. And then we have to conjure up a Gaussian surface that has a couple criteria. So the Gaussian surface has to have the electric field constant on some part of it, if not all of it. So we've got to make up a Gaussian surface on which the electric field is constant. That's equivalent to saying we've got to make up a Gaussian surface on which the electric field is perpendicular to that surface. That's exactly the same result, even though it's tested a different way. But the any other sides that aren't perpendicular and therefore equal or having a constant magnitude electric field on the surface, any of the other parts of the closed surface have to have the electric field be perpendicular to that, so that the that integral E dot dA will be zero. Okay. Now, again, as I said, there's only three types of problems that can be solved. The problems are spherical problems. So whenever you have a spherical distribution of charge, in principle, you can use Gauss's law to solve for the electric field, which is the integrand of the left-hand side. And to do that, you have to choose a spherical concentric Gaussian surface. So in other words, if you're looking for the electric field inside of the spherical charge distribution, then you have to use a Gaussian surface that is spherical and concentric with the existing spherical distribution of charge, and the radius has to be smaller than the spherical distribution of charge. And then when you're trying to calculate the electric field outside of that distribution of charge, you again have to use a Gaussian surface that is a concentric sphere, only this time the radius will be bigger than the charge distribution. So that's one type. Another type is infinitely long cylindrical. Okay. In an infinitely long cylindrical charge distribution, which is like the first integration problem we did in chapter 21 when we integrated Coulomb's law, that was pretty tough. But in a Gauss's law standpoint, that's actually a pretty trivial problem to solve. But with that infinitely long cylindrical symmetry, the Gaussian surface you have to choose is a concentric cylindrical surface. And it's not infinitely long. In fact, it has a very specific length that you might call L or H or something like that. And when you go to do it, what you're going to find out is that since the distribution of charge is along a infinitely long cylindrical piece of wire or whatever, that means at every point the electric field points perpendicular to the wire at every point. Therefore, when you make the Gaussian surface, it needs to be a concentric cylinder of finite length. And the soup label, is what I've been calling it for that cylinder, is the part that gives you the electric field times the area. That's what the left-hand side always equals on Gauss's law. It's some area times an electric field, maybe times a number 2 or something, right? So the soup label is the relevant surface, and in fact, when you do the dot product with the top cap, the dA is that way, and the electric field is perpendicular to it, lying in just the XY plane. And the same thing happens on the bottom, where the dA is pointing down, but the electric field again is only having an X and Y component. So you use a concentric cylindrical uh, surface as the Gaussian surface when the symmetry is cylindrical and infinitely long. And the soup labels are the parts that give you non-zero answers on the left-hand side. The third option is an infinitely large plane. And guess what? When you use an infinitely large plane, we usually use a cylinder for the Gaussian surface as well. Only the cylinder, you could imagine it as if the surface would be this Rubik's cube, but it goes on for infinity that way, this way, and this way. And what you would imagine is maybe this is the cylinder that we're talking about, and we slowly bring it up to the Gaussian surface, and then we let it penetrate so that the flat surface is dead center at the center of this cylinder. Okay. So you're going to have a bottom of the cylinder that's below the infinite plane, and the top of the cylinder is going to be above the infinite plane. And in this case, it turns out that the electric field will be perpendicular to the top and bottom, so that it's actually parallel to the dA at the top and bottom. So the non-zero parts of the left-hand side are the top and the bottom, and the soup label is actually zero. So that's the big trick, because hopefully by me telling you it's really only 3 problems that you can solve, hopefully that takes a little bit of the fear out of it, because I know a big fraction of the scariness of Gauss's law is that I think students look at it and like, I don't know how to come up with these Gaussian surfaces. And then I don't know how the integral plays out on these Gaussian surfaces. Well, my teaching technique shows you what the integrals play out to, but now I'm also letting everybody know that, hey, there really is only 3 Gaussian shapes that you can use. They've got to be a sphere for spherical symmetry, and it's got to be a cylinder for cylindrical symmetry, and a cylinder for planar symmetry. And in those cases, the cylinders, the parts of them play different roles. For instance, when you're doing an infinitely long cylindrical distribution of charge, it's only the soup label of the cylinder that matters. Whereas when you're doing a infinitely large plane, it's only the top and bottom of the soup can that matters, or that gives the integral that's not zero. So hopefully that helps you move forward. I would say just do a Google search, or excuse me, specifically a YouTube search on my specific YouTube channel. Just do a search for the word Gauss, Gauss, and you should see like every video I've ever made of applying Gauss's law. And hopefully that will give you plenty of experience watching them, and then you can try to do them on your own. The hallmark are the let's say maybe not the hallmark. Hallmark would be what you'd look for to make sure that you're doing well enough. What I would say is the test of whether you're doing well enough or not is can you close the video, shut down the video, or close your book so that you're not actively looking at a example and then solve a Gauss's law problem to solve for the electric field. If you can do that with the book closed, you're probably doing it right. You don't have to show all the steps, but for instance, and for me to make sure you understand what you're doing, when you're doing a cylinder, I need you to show me three different integrals so I can see that you know, oh, we're integrating on the top of the soup can, we're integrating on the soup label of the soup can, and we're integrating on the bottom of the soup can. And then the next step would just be 2e times a, and that's literally the whole left hand side. And if you show that, then you're fine. And you do the same thing with the infinite line of charge or the infinite plane. If you do the sphere, if you're doing a spherical symmetric thing, it's only one surface and there's only one integral. So you basically go from integral of e dot dA to just e times 4 pi r squared because r is the radius of the Gaussian surface and it's a sphere, and the surface area of a sphere is 4 pi r squared. Okay. So hopefully those words are helpful. I know it's a lot of words without me writing stuff. So it's better to have this like in audio and video form so that you can look at it a couple times if you misunderstand. But other than that, that's all I wanted to remind you about if no one has any specific questions about Gauss's law or previous stuff. So still no questions? All right. So yes, TCC did cancel classes at 3 o'clock. So really, you definitely don't have to stay past 3 p.m. But what I wanted to do is go ahead and jump into chapter 23. So anybody have any questions before I move on? Again, I don't think you do because I've asked, but just in case, I'm giving you the option. All right. So I'm going to click on in my canvas, I'm going to click on the Access Pearson so I can pull up the book so I can refer to it. Mainly because we're doing a new chapter and I wanted to use the examples that chapter is using. I know it. I've worked out the details of the course and the lecture already, so I can, give you that lecture, no problem. It's just a matter of I want to have the examples ready so I can help you with that. So we are in chapter 23. I'm going to click on table of contents and I'm going to go to chapter 23, which is called electric potential, I think. Yes, chapter 23, electric potential. Okay. So obviously that's a copyright violation if I go putting the book up on my video, so I'm not. But I want to remind you that the first section, 23.1, is electric potential energy and potential difference. The big thing to understand from that is I'm introducing a new quantity called potential difference, which is also called electric potential. But notice in both of those cases, I'm stopping short of saying the word energy because you're used to probably hearing the word potential followed by energy. So if I say electric potential or electric potential difference or electric potential or some other words like that or just voltage, what you want to know is I am referring to voltage and that's measured in the units of volts, and a volt is defined to be a joule per coulomb, and I'm going to explain how that comes to be in a second. But right now that's what I want you to understand is there is something called electric potential that's measured in volts and it's not measured in joules. There is also something called electric potential energy, which is a potential energy and is measured in joules. And I'm going to try to express the difference between those. Okay. So The first section, like I said, is 23.1, electric potential, energy, and potential difference. 23.2 is the relation between electric potential and electric field. 23.3 is electric potential due to point charges. 23.4 is potential due to any charge distribution. So that's where we're going to bring in the calculus and start integrating again. Section 23.5 is equal potential lines and surfaces. So that's a recap of like our first lab where we did, or where we were supposed to do electric field mapping. So we used a galvanometer to find all the equipotential surfaces, which were just lines in that case, because we're dealing with two dimensions. And this is going to bring that back and let you understand how those places where you had lines of zero equipotential, how they tie into the electric field. So that's what Section 23.5, equipotential lines and surfaces is about. Section 23.6 is potential due to electric dipole. So we're getting more into that dipole moment stuff we talked about. 23.7 is how to calculate the E field if you know the voltage, the electric potential. 23.8 is electrostatic potential energy, the electron volts. So that's a new unit of energy that is really good for dealing with microscopic quantities and atomic and molecular quantities. And then 23.9 is really a section that's very, very interesting and super helpful for your understanding how the universe works and how modern technology works. But we're not going to cover that, and I'm not going to test you on it. So sections 23.9, 23.10, and 23.11 are very important, and they're very important to how applications of how these things are done, but I'm not going to ask you questions from it. That's digital binary numbers, signal voltage, TV and computer monitors, and electrocardiograms, ECGs/EKGs. So let us go ahead and get started. I'm going to go ahead by sharing my iPad screen. Just stop me if you have any questions at any time. All you have to do is just speak up, because I know you guys aren't used to uh, me teaching via Zoom. And you don't have to, say anything if you have to leave, just split. It's not a big deal. I'm not even taking roll or anything. I did take roll during lab, but I'm not taking the roll during lecture. So what you're looking at right now is basically the first page of my iPad screen. And what I'm going to do here is explain something to you to help you understand what we're going to do. So what we learned in 241 was that in certain cases you can create a potential energy function. Well, I wrote it out last time for my students. Actually, let me show you exactly what I wrote for my students last time. Here it is. So this is what I wrote for them. Potential energy functions can only exist if a conservative force exists. So you might remember that if you had me for 241, I wrote down F is a conservative force, and that was like condition one. And then I wrote condition two, which is the integral from A to B of F dot dl is independent of the path. And I wrote down three, the closed integral of E dot dl is equal to zero. And I wrote some other stuff. Well, it turns out if any one of those are true, all of those are true. And one of the things that came up in that is that there exists a scalar potential that can faithfully represent the conservative force. Okay, so this first paragraph is about that. It says potential energy functions can only exist if a conservative force exists. We call forces conservative when they have a curl that is identically zero, and such forces lead us to develop conservation of energy laws. The change in potential energy, we call delta U, is defined to be the negative of the work done by a conservative force. So that is what we actually use to define a potential energy function. So for instance, last semester or whenever you took 241, we considered lifting a mass M very, very slowly from a height of zero to some height h. And I had to do it very slowly because I didn't want to give it any kinetic energy. I just wanted to release it enough where it could be lifted. and release it enough again so it can be lifted, and release it enough again so it can be lifted. And by doing that, I ended up going from a height of 0 to a height of h, and I calculated the work done by gravity, and the work done by gravity turned out to be negative m times g times h. So the change in potential energy in me going from h equals 0 to h was the negative of that work. So the negative of negative mgh is just mgh. And by that, we learned that the potential energy function, at least for places close to the surface of the Earth, was just U is equal to mgh. Now we're going to do something similar to that using electricity. And that's what all this stuff down here at the bottom is showing. We see that the work done by a conservative force, F sub c, is given by the integral of F sub c dot dl. We define the change in potential energy, delta U, which is U final minus U initial, and I'm saying B is the final position, A is the initial position, and that's supposed to be equal to the negative of the work done. So I put a negative out here to represent the negative of this work. So that's what's happening. But what we know is we had defined an electric field E such that it was the limit as Q approaches 0 of F over Q. If we keep that in mind, then we can go on and start to figure out what we're going to call our electric potential. Notice I didn't say the word energy. Our electric potential energy is the U that I keep talking about. Our electric potential is the V that I haven't talked about yet. So right here you see the change in electric potential, also called the change in voltage, delta V. We're going to define that to be the change in potential energy divided by Q. The reason why is because we had as a model an idea that we could take the force and divide it by Q. So it seemed reasonable to us we could take the energy and divide it by Q and maybe get an analog to potential energy. And that's exactly what we got. In other words, it worked. So we defined the change in voltage to be the change in electric potential energy divided by the charge. And that means UB minus UA over Q is the change in voltage, and that becomes the negative integral of the conservative force dotted with dl from A to B and divided by Q. But remember, the F divided by Q was the electric field, so we ultimately got this, which gave us this equation. So this is our definition of how to calculate the change in voltage from point A to point B. We just call it the negative integral from A to B of E dot dl. And that is what we call a line integral or a path integral. And those of you who had me for 241 should know to some extent exactly what's going on with that, but I'm going to teach it to you as we go along today as well. I did point out that 1 volt is defined to be 1 joule per coulomb. And you can see that from right here because the potential energy is in joules and the Q's in coulombs. So this is joules per coulomb. That's why 1 volt is equal to 1 joule per coulomb. So that's the big idea behind all of this.
So,
Yes.
sorry, going back to the previous page,
hmm
the thing that's confusing me is the transition from E to delta V.
hmm
Is it, so how can we have a delta U? Is that for like a non-uniform field? Is
Yeah,
that where we can have a delta U? How, what is U?
you are thinking exactly the right stuff. The easiest way for me to show that, though, is to take a specific example, and I think when I do that, it'll make more sense to you. So
Yes,
you
sir.
want to try that?
Yes, sir.
Okay. So what I'm going to do is I'm going to draw. It's technically what we call a parallel plate capacitor. Okay. I'm going to draw one side as if it's a positive plate, and I'm going to use the nice software tool that this notes taking system gives me. So it drew a nice straight line, even though my crap's crooked. That plate right there is going to be a positively charged plate. So I'm putting red plus sign right above it, and everything associated with it I'm going to write as red so that we can keep track of what's what. On the other side, I'm going to put another plate, and we're looking at them edge on. So this plate, you might imagine, goes to infinity behind the page and comes out and goes to infinity towards us as well. And technically, you might also say that it goes to infinity upward and downward. But really, all that matters is as long as we stay near the center of the plate, it's going to act just like the plate is infinitely large. But this plate, the black one, is going to be negatively charged. Now, we did work Gauss's law the other day with an infinitely large plate, and what we got was this result. So let me show you with a coordinate system. So this is going to be our x-axis. This is going to be our y-axis, and this is going to be our z-axis. And my infinite plane is going to be like this. Okay, now it's supposed to be infinite. I don't like that last line. It's supposed to be infinite, so we can represent that by putting a little infinity there, and maybe there, and there. Okay, now what we found for this, and notice it's one dimensional, this or it's two dimensional, this plate, so it has no real thickness. But what we were able to discover in doing this with Gauss's law was that we got an electric field E that is equal to, it's a piecewise function, it was equal to positive sigma over 2 epsilon naught, where sigma was the charge per unit area of the plate, times k hat, and that was for z greater than 0. And then if we went below the plate, that plate's still positive. So being that it's positive, it's also going to push downward on any positive charges that try to get near the bottom of it. So in that case, it's negative sigma over 2 epsilon naught k hat. And that is for z less than 0. Okay. So now that we know that, I want you to forget for a split second about the black plate, and let's just think for a second about the red plate. We know that the electric field has a strength near the red plate of sigma over 2 epsilon naught. So in between these two plates, again, try to pretend like the black plate's not there, but just long enough to figure out in between the two plates, in which direction will the electric field point as a result of the positive plate. To the right, very good. So I'm going to mark that with a red arrow to represent the electric field, and its magnitude is sigma over 2 epsilon naught, which I also wrote in red so you know. Now, I want you to understand that that also means it's to the right outside of the gap between them as well. So because this had no z dependence, it's exactly the same value even to the right side of the black plate. Does everybody get why I can put both of those pointing to the right there? Anybody have any questions about that? Now, obviously, the farther and farther we get, the less accurate the plate being infinite is, but we're going to focus mostly on being really close to the plates. Now, what about the left side of the red plate? In which direction will the electric field point on the left side of the red plate?
Left.
To the left. Very good. And in fact, it will also have a magnitude of sigma over 2 epsilon naught. Now, let's forget about the red plate and think about the black plate. The black plate is negatively charged. So you can sort of think of it as replacing that sigma in this. Think of replacing the sigma with negative sigma. So this one would become negative sigma over 2 epsilon naught, and this one would become positive sigma over 2 epsilon naught. Okay? So to the left of the black plate, which direction would the electric field point due to just the black plate?
It's a black plate with a magnitude of sigma over 2 epsilon naught.
Exactly. And of course, that also means over here we'd get the same thing. Okay. Now, what about to the right of the black plate? Which direction will the electric field point there?
Towards the black plate.
Very good. Everybody following that? And again, the magnitude is sigma over 2 epsilon naught, which generally speaking, you take two identical plates. One's charged, let's say, positive 30 microcoulombs, then the other one will be charged negative 30 microcoulombs. Therefore, the sigmas are all equal and all that good stuff. So, when you look at the electric field in between the plates, you see that they're both pointing the same way, so they add, and you get the net result as an electric field line that points from left to right, just like this. And it turns out to be a very uniform electric field. And the uniform electric field has a magnitude equal to sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which is sigma over epsilon naught. And I'm trying to show here what happens to the electric field when you get near the edges. So right here, E is going to equal sigma over 2 epsilon naught between the plates. Okay? Over on the right-hand side, though, you see that the electric fields are equal in magnitude but opposite in direction. So in this case, E is equal to 0. And then you see on the left-hand side, the same thing happens too. So E is equal to 0. Does that make sense to everyone?
Um,
Okay,
so
go
we
ahead.
have sigma over 2 pointing to the right and also sigma over 2 pointing to the right. Wouldn't it just be sigma over epsilon naught, not sigma over 2 epsilon naught?
Exactly. I thought I know I said it right, but I clearly did not write it right. But thanks for catching
Yeah,
me on that.
no problem. And the other thing, so the two metal plates here would be conductors, right? The whole capacitor is made out of inductors, right?
Yeah, it's normally two big conducting plates that are connected to wires, and then between it, they'll either the simplest case could just be a air or a vacuum between it, but it turns out we get a lot of bang for our buck if we put we call it a dielectric. So when you hear the word dielectric, so you can use that, which makes you sound a lot smarter. But you can say dielectric instead of saying insulator. But that's
Oh,
really all
okay.
it is. It's just something that doesn't behave like a conductor in the conditions that it's subject to.
My question was about like how in the book, and you mentioned it as at the end of the last lecture, they said like the current inside or the charge inside of a conductor would be zero. So if this whole capacitor was made out of metal, it
Ah,
couldn't hold any charge. Would that be like a correct observation, or am I missing?
exactly. Yeah. If you tried to
Okay.
fill between those two plates with a metal, yeah, you'd end up getting no ability to store any charges. In fact, all the charges would run out to the outside edges and there'd be no electric field inside of it. In electrostatics. Now, if you connected that to a battery or to a power supply, then you could actually get an electric field going through the conductor, and that would compel the charges to run through it, not just stay on the outside surface like they do in electrostatics. Does that make any sense to you, Hadi, or did that throw a
Yes, sir.
curveball to you?
Perfect. Thank you.
Okay. All right. So now that we have that as an idea, and you probably know because we did set one up, or at least I told you about setting one of these up in our electric field mapping. But the way you would set it up is you connect the positive terminal of the power supply to the left one, which is the positive side of the capacitor, and you plug the black one, which is the negative side of the power supply, to the black plate, and that would make it negative. So you automatically think that the left side is a high voltage and the right side is a low voltage, and you're absolutely right. What we're going to do now is I am going to take a charge, and it's going to be a positive charge, and I'm going to put it in this diagram right here. Oops, I went to do a different color. I changed it to blue and it didn't change the blue. There it is. Okay. So I'm going to put a positive charge right there, and that's location A. Now, what I want you to understand is the the definition of electric field is that the electric field points in the direction that a positive charge would be compelled to move if it was placed in that location. So the fact that these green lines show the electric field pointing to the right means that if I put a positive charge in there, it's going to go the direction of the green arrows. So on its own, spontaneously or naturally, whatever you want to call it, that positive particle is going to move from A to B. Does that make sense to everyone? Do y'all understand that naturally the positive charge is going to run away from the positive plate and run towards the negative plate? So you can think of that a couple different ways. One, you can think of it as it went the direction of the electric field, which is the definition of how electric field direction is defined. But you could also think of it as, oh yeah, that left plate is just packed with positive charges. So the positive charge wants to get the heck away from them because we know like charges repel. But not only that, that black plate over there, that's just packed with negative charges, and positive charges are attracted to negative charges. So it's also natural for it to go to the right. Because of that, we can say the work done by Coulomb force and remember, the Coulomb force is the conservative force. We know it's a conservative force because it looks exactly the same as the law of gravity. And we used the law of gravity back in chapter 6 to learn, or chapter 7 to learn that it had a potential energy and that the work was equal to the negative of the work, or excuse me, the change in potential energy was equal to the negative of the work done by the conservative force. So now I can see that the magnetic, or excuse me, the electric field between the plates is a uniform electric field. Therefore, when I try to calculate something like work equals the integral of F dot dl, the F is a constant, so I can pull it right out in front of the integral. In fact, the F is the charge, which we'll say Q, times the electric field, which we'll call E. We know of course it's sigma over epsilon naught, but we're just calling it E right now. So there's our force part, and I will indicate that with some little arrows or some little red things here. This is just F. And remember, we were using work is equal to the integral of F dot dl. And what we found was F equals a constant. Implies work becomes the constant times the integral of dl. Well, we can say this distance is just d. That's the separation distance between the plates, in which case the integral just becomes the integral of dx from x equals 0 to x equals d. So in order to get the work, all we have to do is multiply the force, which we said was QE, times D. So that is the work done by the Coulomb force. The Coulomb force is pushing it to the right. It's going to the right, so they have the same sign. So that's the work done by the Coulomb force, which equals the work done by the conservative force. So we've got that. We also know that the change in potential energy is defined to be the negative of the work done by the conservative force. And that's William. Okay. So now that we have that, we can say that clearly delta U is equal to negative Q times E times D. Okay. And what we can do is we can think, did the potential energy go down or up in the positive charge moving from, and the positive charge, by the way, is Q, moving from A to B? Did the potential energy go down or up? The charge moved on its own from A to B so that U sub B must be less than U sub A. Okay?
Is is that so? From my understanding, the potential energy is the ability to do work, correct?
Mm-hmm.
So when it moved away, there is more of a distance, meaning less of a force being exerted by the electric field since our spirit is in the bottom. So it
Mm-hmm.
has less force and thus is able to do less work. Is that why it has less potential energy?
Ah, no. So what you're thinking about, especially when you use 1 over r squared, is you're thinking about a charged particle near a point particle. And yeah, that electric field falls off like 1 over r squared. So yeah, as you move it away from a point particle, the electric potential is going to get smaller and smaller. The same thing's happening here, but in this case, the electric field's a constant because it has no dependence on z or x or y or r. So,
Right.
but it turns out just by the nature of what we know about potential energy is things move from discomfort to comfort, and discomfort can be represented by high potential energy. Just like you're less comfortable taking a nap on the top of a telephone pole than you'd be on sitting on the ground, right? So that angst or that anxiety that you have from being up super, super high is consistent with you having a high potential energy, just like this positive particle being next to this positive sheet of positive charges. It does not feel comfortable. It's packed up against a bunch of things that are trying to make it leave. So it naturally goes away from that spot to a spot that has a lower potential energy. So what we've realized is by this drawing and by our understanding of Coulomb's law, electric fields, and how charges interact with electric fields, we've realized that UB must be in fact less than UA. And since we have that, we can say that delta U, which is U final minus U initial. That's always what delta is unless I explicitly tell you otherwise. And we know that U final was UB, and we know that U initial was UA. So the fact that we know UB is less than UA, we know that delta U would be, in fact, less than 0. And notice that is exactly equivalent to or consistent with uh, delta U equals negative Q E D. Because, like I said, Q is a positive number, E is a positive number, D is a positive number, and then you got to multiply it by a negative, so you get a negative. Okay? So we've got our home base there, and what we've just decided is like all things in the universe, positive charges go from high potential energy to low potential energy spontaneously. Now, what I want to figure out is what is the change in voltage? So, what is the change in voltage, which is also called electric potential difference, all that sort of stuff. That is delta V is equal to, and we actually define it to be delta U over Q. So what that means is we're going to have UB minus UA, that's our delta U. All of that is divided by Q, and we could call this UB over Q minus UA over Q. And because delta V starts with a delta, we know that is V final minus V initial. So we can also say it's VB minus VA. Does that make sense? Now that we have that and we know that delta U is negative, we can see that the delta V is actually going to be negative as well, because all we're going to do is divide it by a positive quantity. So we can now reach two conclusions. Here they are. One, like all matter, positive Q spontaneously moves from high potential energy to low potential energy. So that's not really a conclusion that we needed. It's just more of a confirmation that of something we already knew. That positive particles move from high potential energy to low potential energy all by themselves. They don't have to be, you don't have to come along and cause it to happen. All you have to do is let it happen. Here's the part that we didn't necessarily know. Positive charges move spontaneously from high voltage, which again can be said to be high voltage, high electric potential, high electric or high potential, anything like that, from high voltage V high to low voltage V low. Okay, so that's a big deal. That's something we learned. We know, for instance, when we picture a battery connected to a wire, we pretend like the battery in that has the positive sign next to it, which is the the one with the little bump up on it in the case of AA, AAA, C, or D batteries. So we can sort of picture the positive charges in the wire running away from the positive end of that battery and trying to enter the negative end of that battery because one, it's going from high potential energy to low potential energy, but duh, we already knew that. But two, because it's running from high voltage to low voltage, we sort of knew that, or at least we've been pretending like we knew that whenever we pictured charges going through a wire. Okay. But what about a negative particle? So, conclusion for a negative particle. So if I go back to here and instead of showing a positive particle, let's say we put a negative particle right here. Okay, notice I did the exact same thing I did before. Of course, this is going to be B and this is going to be A. And what we know is the electric field is defined to point in the direction that a positive charge would be compelled to move. And therefore, a negative charge would go exactly the opposite way. We know that because the force is equal to charge times the electric field. So if the electric field is a vector that points to the right, if we multiply it by a charge that's negative, we get a vector that points to the left. So this negative charge is going to move of its own accord from B to A. Does that make sense to everyone? That the negative charge, we could put it right next to the black side and it would run away from that and then run to the red side. Does that make sense to everyone? Gotcha. Okay. So now that we have that and we know it's for a fact, we can use the same arguments we did before and make the conclusion that one, like all matter, negative charges naturally, so I'm just using a different word than spontaneously this time, naturally move from high potential energy to low potential energy. So again, we didn't really learn anything new there. We already reached that conclusion back in chapter 7. But here's the new part. What we saw is that the negative particle moved from B, which was a low voltage side, as we had already concluded from the positive one, and moved to a high voltage side. So negative charges travel from flee from low voltage and toward high voltage. Okay. So, in the negative particle going from A, or excuse me, going from B to A, that said delta U was, excuse me, delta U was, oops. Oh, I don't know what happened there, but that was not good. All of a sudden, it just like started drawing a text box. I don't even know how it got there. Okay, so I'm going to stop that. So I want to delete that. Delete. Okay. I don't know what's going on. But anyways, delta U is going to be less than, oops, might be helpful if I use red still, is going to be less than 0, and I don't know why it's still showing me black even though I've got it selected as red. Dang it. I see why now. I just saw that it's writing everything in there. I don't know how I got on this stupid thing where it's putting in a text box that I don't want. And I can't figure out how to get rid of it. Let's try this. Nope, that's not good either. Let's erase that. Show the keyboard. Let's delete that. Delete that. Okay. Okay, now I'm going back. Let's see. So, in the electron moving from B to A, we found that that was a decrease in potential energy, duh. But we also found that delta V was actually an increase. So that's a really big deal. And of course, we know that because delta V is equal to what we saw before was we got delta V was just delta U over Q. But delta U was negative QED. And now we're dividing by the negative. And in this case, we're actually getting the Q's canceling out, and we'll have a negative there. So it actually gives us a positive in this case. Actually, let's kill that. But that's the main thing I wanted you to learn is one, we now have a unit called the volt, 1 volt, and that's defined to be 1 joule per coulomb. Positive particles go from high voltage to low voltage. Negative particles go from low voltage to high voltage. And because of that, we now have a new way of solving problems, just like when we did kinematics and then we went into dynamics, which used vector quantities to solve Newton's second law of motion. That was all well and good and got us a lot of stuff, but then we were able to work predominantly with scalars when we introduced work and energy and conservation of mechanical energy and that sort of stuff. Now we can introduce the scalar quantity voltage, and by doing that, we can work a problem with scalars instead of vectors, and life's a lot easier. Go ahead, Hadi.
So when we're talking about a voltage across a resistor,
Mhm.
can we say that's like a measure of how much work one electron had to spend to cross that distance?
Yeah, that's sort of a way of thinking about it. Yeah, and in fact, it works out because we can actually. It turns out the equations that dictate how a electron going through a circuit behaves are identical to the equations for mechanical and kinetic energy, so that you can always think of a high voltage as if it's a high height, and then the particles go downhill. So the positive particle would, for instance, go downhill, whereas the negative particle would actually go uphill. So just to give you an idea what I'm saying here, we would normally draw a circuit like this. We'd say this is a battery. The long line up here is the positive side. The short line is the negative side. And we could say that it come out and then it runs into a resistor, which that's the symbol we use for a resistor. And then that wire goes back and runs into the negative side of the battery. Uh, we can think about it that way, but now there's another way we can do it as well. We can imagine this line right here as perfectly horizontal, and then we'd say there's the little short line, and then we draw up here the long line. And from this, we'd say, okay, well, now this is perfectly horizontal, but notice how much higher I am. And now this part of the line is like this part of the wire. And this part of the line is like this part of the wire. And then that's it. So you can see that basically we're going left. Oops, hold on. You can see that basically we're going level, going level, going level. We get to the battery. The battery picks us up to this highest height. And now we go lower, lower, lower. Technically, we're going lower all the time because the wire does have some resistance. It's just really, really small compared to this resistance. So we pretend like it's perfectly level and it stays level and it stays level and it stays level and it stays level. Technically, I should probably draw that this way to show it stays level. And then the resistor brings it down to low again, and then we're back at level and we're back where this is. So, yes, that up and down hills, we can think of it just like doing work, which would cause something to go up a hill, or uh, the system do work on the particle, which makes the particle go downhill, that kind of thing. Does that make sense, ID? Or did that make it worse?
No, no, I get that analogy. Thank you.
No problem. Yeah, and if we're actually technically drawing this correctly, then this has to be like this. And in order to do that, the resistor to do something like that. So now it looks a little bit more like level and then shows the resistor, even though it's a crappy drawing, you can see that it definitely changed the height. All right. Well, I think that's good enough for right now. This is already 3:30. You guys are supposed to have class over at 3 o'clock anyways because of the weather. So you can go ahead and split. I'll probably put a couple more videos up while you're either on break or this weekend or whatever. But remember, you do have spring break next week. So I'll put these videos up, and I just want you to check them out before you return to class 2 weeks from now. There will be, like I said, an online test that's due the Sunday before we come back. So try to knock that out. You can knock it out this weekend, or you can wait till you get back from break and knock it out Sunday night or whatever. I think what I'll do is I'll make it due Tuesday night instead of Monday night, or instead of Sunday night, I'll make it due Tuesday night. That way, if anybody really is doing something for fun for spring break, you don't necessarily have to do it immediately upon coming back. Okay? You guys are free to go. Thanks for coming, everybody.
Thank you, Professor.
All
You're
right,
welcome.
have a good day.
You too.
Have a good one.
Thank you. You too.
Have a good day.
You too. Thank you.
I just got one quick question.
What's that?
So for that negative charge plate, right?
Mhm.
What I'm thinking is electrons are moving through it,
Okay.
and then for the positive charge, what's happening there? Is it just a lack of electrons, or
Okay. So what's really going on is it turns out the nucleus of the atoms that make up, say, the copper wire, you can't do hardly anything to alter a nucleus of an atom. They're a whole different energy group than stripping electrons. So what happens when you have a wire is you have individual nuclei of atoms all arranged in a little lattice like beads on a wire, and then another layer of wire, and then another two layers of wire above that, and another two layer of wires below that, and then another layer of three sets of wires and another layer of three sets of those nuclei all stay in the same spot within the wire. But the electrons in conductors are not being held very tightly to their nucleus, so the electrons are free to move around the whole wire. And because of that, they're actually the ones doing the moving. And when you put a battery on a wire like we have drawn in this picture, then what happens is this negative side right here compels any free electrons to move this way. And the electrons just keep moving this way, this way, this way, this way. and then they come back, in fact, to the positive side. Now, there isn't necessarily a bunch of electrons leaving the negative side of the battery or coming back into the positive side of the battery, but the main thing is the battery establishes electric field in the wire so that the electrons are compelled to continuously move that direction. So what we do is we picture conventional current, which is the direction that positive charges go, and we pretend the positive charges come out of the positive end and go through the resistor and then come back and return to the negative end. But in reality, it goes the other way. The good news is there's only one type of experiment you can do that would contradict you on that. And we don't do that very often. So you can completely pretend that conventional current is reality. That thing that you do that would detect it is called the Hall effect. And basically, if you put, let's say, like a magnetic or a electric field perpendicular to the wire, you would tend to make the charge carriers, if they're negative, they're going to move along the bottom edge of the wire. But if they're positive, they're also going to move against the bottom edge of the wire. And if you measure the voltage difference from the top edge of a wire to the bottom edge, the sign of that voltage would tell you whether it's the positive ones that are moving or the negative ones are moving. And when we did that, called the Hall effect, we found out that it was the negative charge that are moving.
Okay.
Did that make sense?
Yeah. Yeah, I was more used to the conventional, like
Mm-hmm.
the reality movement in my circuits class. So
Yeah, that's the way we pretend, and it's a little bit easier to use, but sometimes I revert back to the actual reality just to let them know because it doesn't, once you learn how the nucleus is so much heavier than the electron and so much bigger than the electron, it doesn't make much sense to say them big suckers are moving around, and it really doesn't make sense when you start talking about the wire being solid because the nature of a solid material is you've got atoms sort of in a little jungle gym, and
yeah.
that's what makes the solid.
Yeah. Okay.
Okay.
Yeah.
Hopefully that
Thank you.
helps. We'll get into more details of the circuits as we go along, but this is the first part of that. And let me know if you have any other questions.
All right. Thank you.
All right. See you,
Have a good
Dan.
day. Yeah.
How about you, Derwin? What's going on, bud? He might be gone already. All right. Well, I will call it a day. I appreciate you guys coming. Thanks, and have a good day.
Thank you. Sorry, I was in the other room.
Oh, okay. That's no problem. No problem.
Yeah, no,
Did
I
you
was
have a
brief.
question before
I
I
had to
left?
make something, get something prepared for later. I'm so sorry.
Oh, no problem.
But I was here. Thank you for the class and everything.
Good deal. And you don't have any questions before I go?
No, sir. No,
Okay.
I might email you regarding the lab, just like if I have any questions.
Gotcha. Did you hear what I said about the online test?
Uh,
I'm going to
only.
make it due Tuesday night after you get back from break instead of Sunday night.
Okay, awesome. Thank you very
Okay.
much. I
All right.
appreciate
See you,
it. Have
bud.
a good one. Take
You
care.
too. Bye bye.
Bye.